Alright, so here's a problem. We want to write the equation for slope and displacement for this beam. As we've talked about in class, you can see that since I have a continuous load over the whole range of the beam, that I can write a continuous moment expression. So I should be able to find a continuous equation for slope and displacement. Probably to get started, we're going to need some reactions, don't you think? So I'm going to cheat a little bit and use the structure here as my free body diagram. I'll call this AY and BY. You know, before I do that, let's talk about it this way. How do you think this structure is going to displace? What's going to happen at the pin and the roller? They're free to rotate, right? So more than likely, you're going to get a displacement that looks something like that. And we're going to know that what's true at A? Is the slope 0 at A? No. Is the displacement 0 at A? Yes. And then over here at B, is the slope necessarily 0? No. But the displacement is. So we're not going to have any condition on displacement, on rotation, but we have 2 on displacement. Also, I'm going to cut the structure to draw my moment diagram. And which side do we want to work on? The left side or the right side? I don't see any advantage. I think the left side will probably be easier because I can easily measure that distance as just x to the cut. So let's work the left side. Since we're going to work the left side, I just really need the reaction at A. So how can I find the reaction at A very quickly? I need to, can't sum forces in the y direction, that would be a poor choice, but I can sum moments at B. So let's do that. So I'm going to use right-hand rule for my sign convention, and I'm going to sum moments at B and make sure it's in equilibrium. I want to do something with this distributed load to make it a little easier to handle, so I'm going to get the concentrated force equivalent. And what is the value? Well, it's a rectangle, so it's going to be base times height, which in this case is WL. And what's the distance from either end? It'll be L over 2, right? So when I sum moments about B, this load is going to create what? Positive or negative moment? With my sign convention, it's going to be positive. So there's the force. And then the distance from B to the centroid is L over 2. And then AY is going to create negative moment at a distance of L. This should not be a surprising result, but you see that AY is going to be WL over 2, basically half the load. And again, that's something we've seen before. You'd expect with a uniform load, with this kind of support system, that half the load will go to A and half the load will go to B, and equilibrium says that's true. So now I'm going to cut the structure at this distance x. I'm going to apply what I know to be AY, which is WL over 2. I have the distributed load still applied on my structure. It still is W. And at the cut, I'm going to be interested in the bending moment. So there's my positive bending moment. Don't forget that this distance is x. So we've done this a few times before. So what is going to be the concentrated equivalent for this section of the uniform load? Well, again, it's still a rectangle, so it's going to be the base dimension, which is x, times the height, which is W. So this is going to be a force of Wx. And what's the distance from the cut? Half the length. The length is x, so it's going to be x over 2. So I'm going to find my moment. So again, I'll sum moments. As usual, I'll assume right-hand rule. And I'm going to make sure that at this cut surface, there's no rotation. So looking at this free body diagram, this moment is what? Positive moment. This force Wx about the cut, positive or negative moment? Positive. So I've got Wx, and what's the moment arm? X over 2. And then I get over to this force, which is WL over 2. That creates what kind of moment about the cut? Negative. And it has a moment arm of X. So I should be able to write my moment expression. Let's see. You'll notice they all have a W, so maybe I'll pull that out. And then the first term will be minus x squared over 2. And the second term will be plus XL over 2. I didn't pay attention. I guess I could have pulled that 2 out also. I may do that later or in the next step. Now, before we get going, does this work? Is this an appropriate moment expression? Let's go back to the original problem. Do I know the moment anywhere in the structure? What's the moment at A? Should be 0. So the moment at A is when x is equal to 0, should be 0. Does my equation say that's true? When I put in 0 for x, I get 0. So that's good. Where else do I know the moment? What about at B? Yeah, so that would be at x equal L. Should also be 0. And if you plug in x equal L, you get L squared over 2 minus L squared over 2 plus L squared over 2. Again, 0. So I'm feeling pretty good about my moment equation right now. Now, a couple weeks ago, this would be the end of the problem, right? Now it's just the first third. Isn't that exciting? I think it is. So now what do? The method is called direct integration, so we should integrate. So let's do that. So I know the first integral will give me the slope, so the integral of my moment divided by EI should give me the slope. So I've got this W, and I've got this 2, and I've got this EI, so I'm going to pull out W over 2EI. And then what I'm left with is the integral of minus x squared plus XL. I'm integrating in x. So let's do that. So again, my constant stays the same. And what do I get? This becomes minus x cubed over 3 plus x squared L over 2, and I generate an integration constant. Now with these boundary conditions, I don't know anything about slope. I do want to mention at this point, though, that with this distributed loading being uniform and this geometry, what do you think the slope is right in the middle? 0. So that is a possibility for this particular case that you could evaluate and find C1 when x is equal to L over 2. But I'm not going to do that. I'm going to say, in general, that may not be true. If I change this loading to something else, or there's a little bit of an overhang over here, things will change. So I don't think that's the safest way to go. I think the best thing to do is just to leave it there, integrate it again, and apply the 2 displacement constraints. Mr. McBride.
You said this step that we're doing now, and we just started the method of what? Integration?
Direct integration. So we now know that if we integrate the shear we'll get our displacement. So there's my shear equation, so let's integrate that. So again, I've got that W over 2EI sitting there, and I'm going to integrate x cubed over 3 plus x squared L over 2 dx plus I'm going to integrate C1. Another thing to notice is that the order of these terms is the same. Remember, x is a length, so the first term has length cubed. The second term has, well, there's x squared, and another length makes it cubed. So these terms have the same order. So when you do this integration, make sure you check that the dimensional order of each term is the same. That's how we can add them together. Again, this is not going to be a difficult integral to do. They're nice and these polynomials are nice and neat. So there's my constant. So let's integrate the first one. So I'll have minus x to the 4th over 12 plus x cubed L over 6. What's the integral of C1? C1x. And then we get another integration constant, C2. So I have one equation in displacement, there it is, with two constants. But I have two conditions. So let's apply those. So I know that the displacement at x equal 0, that's A. What's that displacement equal to? 0, right? There's one of my conditions. Apply that to this equation. Well, 0, 0, 0. What am I left with? C2. So what is C2? 0. My second expression, or my second condition, is that at x equal L, which is over here at B, I also have no displacement in the y direction. So now I got to plug in x equal L all through there. So let's do that. So I've got W over 2EI, and then when I plug in L here, I get minus L to the 4th over 12 plus L to the 4th over 6 plus C1L, and what's C2? It's already gone to 0, right? So I got one equation and one unknown, C1. So solve for C1. So what is this going to be? You got L to the 4th over 6, L to the 4th over 12. That's 1/6 is really 2/12. So this becomes L over the 4th divided by 12. If I run that all out here, I get W L over the 4th over 24 EI, and then divide it by L, and then move it to the other side. I should get minus WL cubed over 24 EI. Is that right? That means I'm done. So what's my expression for displacement as a function of x? Well, it's this thing plus C1x. Now, this is where you can get creative and you can start trying to pull things out and match things up. This 24 in the C1, I can get 24s here too. I'll just pull that 12 out. This will be a 2. So I'm going to end up with a W over 24 EI. By the way, at this point, you don't have to worry about this. For me, this would be good enough on the exam. But just to finish this problem, make it kind of neat, I'll end up with minus x to the 4th plus 2x cubed L minus XL cubed. So that should be the displacement of the beam. Now we should check it, right? We know the displacement at A is what? 0. And A is at x equals 0, so I put at x equals 0, I got 0, 0, 0, yeah, that works. And also at x equal L, point B, it should be 0. Plug in L, I got L to the fourth, plus 2L to the fourth, minus L to the fourth, yeah, that's 0. Seems to work. It matches at the ends. So where's the maximum displacement? We kind of know what's in the middle, but mathematically, where would be the maximum displacement? Where the slope is 0. Do we have an equation for slope? Yeah, it was right here. And it involves C1. So now I can write my equation for slope. It should be the derivative of this, right? If I go back up here and look at my slope equation, I'm going to pull out that 24 again. So I'm going to get W over 24 EI. And my first term, let's see, that would be 4, so that's going to be minus 4x cubed plus 6x squared L minus L cubed. I think that's it. Did I do that right? I think so. So in general, what we would do is we would find where the slope was 0, find the value of x. Basically solve this equation for where the roots are. And once you know that root, you'd plug it in here and you'd find the displacement. So remember, our maximum displacement is going to occur when the slope is 0. So you'd have to first solve this equation to find where it's equal to 0. And when you're at home and you got all your resources with you, that's not a hard thing to do. And I think if you did that, you would easily find that L over 2 is the right answer. In fact, if you put in L over 2, that will go to 0, and then you would evaluate the displacement of L over 2 and get the maximum value. So any questions about that one?